In this fifth video for Chapter 5, we're going to be taking a look at something called electric potential, otherwise known as voltage, and we're going to get there in a moment, but we do have two last examples just to finish up from when we were looking at just electric potential energy. And I just want to go back actually and take a quick look at example number 4 and just highlight one little issue here that we did talk about in the video. The reason why we can't just do straight up forces and kinematics is because the force changes as this proton is moving from location A over to location B. Even as it moves a few millimeters, we're already going to be farther away and the force changes, so we have to go with an energy method, but then the energy method actually works very, very well. So we have two more examples just to finish up with potential energy, and then we'll move on to just looking at voltage. So this is number 5, and it's an issue of what we call superposition. There are a couple of forces that are going to be applied to this electron, or sorry, this negative 8.5 millicoulomb charge as we move it from location A 6 more meters down the road to location B. It looks like, just in terms of that person's effort, they're going to be really having to push that thing because it doesn't want to leave the 3.6 microcoulomb charge because the positive and negatives would attract. And it doesn't want to get near the negative 2 microcoulomb charge. So for a couple of reasons, this person doing this work is going to have to push pretty hard. What I do know is the force would be changing, so I definitely want to rely on conservation of energy. I'm going to go with my plan of EPI, that's what we looked at last day, how to find that potential energy, plus EKI, plus the work from that person is equal to EPF plus EKF. And now we can just go through and take a look and see which terms we actually need. It doesn't say that this negative 8.5 millicoulomb charge, right, that's this charge that's right here, doesn't say that it has a running start or that it needs to have a running finish. So I'm going to scratch off the kinetic energy terms, the EKI and this EKF. We don't need either of them at all. But what we do need to do is respect the fact that there is some potential energy in this handshake between that positive 3.6 and the negative 8.5 millicoulombs, and there's some potential energy in this handshake as well. And we have to put both of those in. So there are actually two EPIs. So I'm going to have an EPI plus another EPI. And the same thing is true in the end. There's going to be an EPF and then another EPF. And I just have to make sure I superimpose those two energies to get the total story. So the calculation would look something like this. And I'm not even too worried about what the answer is. It's the setup that's more important to me. But I would be going for potential energy K, Q, Q all over just an R. So I would go K and then trust the math. If there are any negatives, go ahead and put them in. I've got a 3.6 times 10 to the negative 6. Having a little energy handshake with the negative 8.5 times 10 to the negative 3. And that arrangement of charges is located 18 meters apart initially. So I'm going to put on top of 18. But there's another initial potential energy. This is still initial. I've got a K and then the negative 8.5 times 10 to the negative 3 for milli, but then there's the negative 2 microcoulombs, 10 to the negative 6. And at the beginning of the story, those charges are 6 and 36. They are 42 meters apart. So that's just at the beginning of the story. Then I've got this person there that's going to go and do some work. Okay, that's the left-hand side of the equation. And as you can see, I've kind of run out of room. That's okay. I'm just going to word wrap this around and we'll finish the rest of the equation off. Now I'm going to put in the final potential energies, right? Plural because there are two. So I have K 3.6 times 10 to the negative 6 and the negative 8.5, 10 to the negative 3. And at the end of the day, those charges will be 18 plus 6 more. They will be 24 meters apart. And then one last potential energy. So you can have multiple potential energies in your story. That's the key point about this example. There's nothing wrong with that at all. It just takes a little bit more calculating to do. but we can definitely add those all together. And then we have the -2, 10 to the -6 for the micro, and at the end of the day, in the final state, they will be 36 meters apart. So it's a little bit long, but it's not tremendously hard to do. We can throw the values into our calculator. If you're curious and you want to try this out, just to make sure that it's going into your calculator correctly, it should be around 4.4 joules. Okay, one last one. One more story where the force is going to be changing and we're going to have to rely on some energy. We're shooting a proton. Maybe this is at like a particle accelerator like down in Vancouver at Triumph, where they shoot protons. Maybe we're going to shoot this proton towards a sodium nucleus. We're going to try to actually strike this sodium nucleus, so it'll be interesting to see if it gets close enough to this nucleus where it can actually be striking it and maybe causing it to fracture. The proton does not want to get near that nucleus because they're both positively charged. So there's going to be some force of repulsion there, and that force of repulsion is going to grow. And I'm curious to know, how close can we get? I'm wondering whether we can get to within the radius of that sodium nucleus. We're told that it starts a great distance away. And, to be honest, that could be just like 20 meters away. That'd be fine. But when they say great distance, I guess we can say, oh, that's like infinity for distance. And at that great distance, the velocity is 2.1 times 10 to the 7 meters per second. So it has a lot of kinetic energy at the beginning, and we're going to allow this thing to go closer and closer and closer until eventually it just stops, right, as that force of propulsion grows. And so we've got this Q1 and a Q2 that are trying to get really close together, and they're going to be converting that speed, that kinetic energy, into potential energy. The force of repulsion, there definitely is one, right? There's going to be a force of repulsion back like this. That force grows as you get closer and closer, so don't try to do kinematics. Instead, we're going to have to rely on conservation of energy. So EPI plus EKI plus any work from an ELF running behind it, pushing it, is equal to EPF plus EKF. Okay, which ones can we throw away? Well, it did say they started a great distance apart. So if they're a great distance apart, there's no energy in that handshake. There's also no ELF running behind this thing pushing it. We're just going to rely on that kinetic energy to get us there. And then eventually we will run out of speed. We're going to run out of kinetic energy. So if I was doing this question, I would be converting my kinetic energy. So I'd have 1/2, and then they said it was a proton, so I go and just dig up that value from my formula sheet, 1.67, 10 to the -27, with a speed of 2.1, 10 to the 7 squared. There's my kinetic energy initially, and it gets converted into potential energy in the end. So K, now the charges. One of them is a proton, 1.6, 10 to the -19, smallest charge you'll ever see in nature. And then the nucleus over here, it's 11 protons. Some neutrons too, but they don't count electrostatically. So 11 protons, 11 times 1.6 times 10 to the -19. And I'm curious to know this R value, this separation distance. And I ran the numbers, you can double check yourself, and I actually got 6.7 times 10 to the -15 meters. The number's not all that important, unless you're wondering, does it actually strike the nucleus? You'd have to go and check the size of a sodium nucleus to see if that's within its radius. It's the setup that's the most important thing for us right now. Don't try to use forces and accelerations because the acceleration is growing on the way in. So we needed to finish those last two examples up from just looking at potential energy. And now we can look at something that physicists kind of do a little bit of a play on words here. The topic from last day was potential energy, and now we're going to take a look at electric potential. It's not quite like they're saying potential energy. They're getting close, but they're just saying the word potential. So you're just about there. You're pre-calculating this potential energy, but you're not quite figuring out potential energy when you figure out potential. And a lot of people, they just call it voltage. So let me tell you some things about this pre-calculator of electric potential energy. So just as a definition, what are we talking about here? Voltage is the potential energy, which is strange because I just said it wasn't that, but it's the potential energy. Let me finish this off. Per charge, Q2. Okay, well, why do we need to be doing this? Why are we worried about all these definitions and things? Well, it's a nice little pre-calculation of energy. It's basically a warning about energy. Just like field was a warning about force, voltage is a warning about energy. And if it's supposed to be some fabulous warning, then we should be able to very quickly find potential energies later. And so we can find EPs. And we like to put the P on there just so we don't confuse it with electric field. So the potential energy between charges 1 and 2 can be found very fast by taking the value for Q2, if we finally know what it is, and multiplying it by this, the voltage caused by charge number 1. And you'll see in a second here exactly what that looks like. Voltage is, well, the good news here, voltage is a scalar. There is no worry about direction here at all. We don't have to be figuring out north, south, east, or west, or any angles. Just doesn't happen, just like it didn't happen for potential energy. The units for voltage, rather unusual here. The units for voltage are volts. And you might go, whatever, that's not that unusual. Well, yeah, it is, to actually have the quantity and the units basically going by the same word. That's like kind of saying, what's the distance to Vancouver? And somebody says, oh, it's 400 distances, right? The distance is the quantity, and kilometers or meters are the actual units, but we actually measure volts and volts. It's a bit strange, but that's what we do. I can tell you that 1 volt, that's what we say. I should write it as a capital V because it's named after somebody. 1 volt is actually 1 joule, also named after somebody, of energy for every 1 coulomb of charge, also named after somebody, so we'll capitalize that. All right, now, are there some nice quick equations for figuring out these warnings about energy? And you bet there are. Last day, we were looking at potential energy. We try to remember to put a P on there just so that we don't confuse it with just a straight up capital E for electric field. So the potential energy between charges 1 and 2, we don't usually write the 1 and 2 in, but I'm going to write it this time. Saw last day, this was K, Q1, Q2, all over just an R. Now, if we take this equation and just rearrange it a little bit, it looks like the voltage caused by charge number 1, the warning we have to tell people about because charge number 1 is around, would be potential energy from 1 and 2 together with the Q2 information stripped out. So here's the equation. The voltage, the warning about energy because of charge number 1, is K Q1 all over just a plain old R. It's very, very similar to field, which was KQ all over R squared, but this one's only got an R down in the bottom. Just like potential energy only had an R down in the bottom. Okay, let's put together everything that we've seen now in this chapter. Okay, we can do it on this one page, and we'll be able to see all 4 major corners of the chapter right here. So here's the story. Q1 is 1.125 microcoulombs, and I want you to think about it as being there first. That's why it's number 1. It's been there for a very, very, very long time. And over at this spot 15 meters away, I have this place where sometimes I'm going to have nothing there. So I'm going to cover this charge up for a minute. It might look like that, where I say, oh, well, location B is right here, 15 meters away, just to the side of it. And other times I'm going to say, oh, well, it's not just an empty location. There's actually something there. There's actually a 4 coulomb charge there. And so we'll kind of go back and forth here between saying, oh, yeah, Q2's there, and also saying, well, Q2 might arrive. Right now there's this empty parking stall. So let's see what all 4 corners of the chapter look like. First of all, I'm going to reveal the Q2, and we'll talk about the very first thing we saw in the chapter, which was Coulomb's law. So what's the force on Q2? To get my grammar right, I probably should say due to Q1. Q1 causes this issue where there will be a force on Q2. So that force between 1 and 2, if you want to, you can name it like that. Force that happens because of 1 and 2. It's a vector, so we'll have to think about the direction with our head. You would be going with K, Q1, Q2 all over an R squared. I'm just going to tell you the value. It ends up being 180. I don't mind telling you the numbers, but let's talk about the more interesting stuff. The units. Well, it's a force, so it's measured in newtons. Direction. You got to use your head actually and think about it. Which way would Q2 get pushed around? Well, two positives would repel, so Q2 will get pushed to the right. So for that part, no math, just use your head, just think about it, the fact that two positives would repel. And be cautious. In this equation, you have to remember to go with an r squared. Okay, great. Then the second thing we saw in this chapter was how you could actually warn people about that force. You could say, hey, what's the warning? What's the electric field at location B? So now I want you to imagine that there's nobody home. We're just going to cover this up. There's this empty parking stall at location B, and we want to warn people that if you go and put charges there, they're going to get pushed around. Like a 4 coulomb charge gets 180 newtons of push on it. So what's the electric field? Maybe I'll call this E1 at location B due to Q1. So Q1 creates something that we need to warn people about. So electric field 1, capital E with no P on it, just capital E. It's a vector, so we'll have to put direction in too. We would go with K, Q1 all over an R squared. No Q2 in there. The value ends up being 45, but let's talk about the more interesting stuff, like the units. It's a warning about newtons, so it's actually newtons per coulomb. And then for direction, we would ask ourselves, if you did put a positive there, like if you put a little proton at that location, which way would that proton get shoved? And the answer is, oh, well, to the right, much like that 4 coulombs got shoved to the right. So again, for that part, you use your head and make sure that you go with an r squared down in the bottom. So the E, the electric field, was just a warning about force. And knowing that 45 number can be very handy because later on you can quickly find forces between two charges. Once you know who arrives, you can put that Q2 in and multiply it by that first electric field. So indeed, you can come up with that answer of 180 if you say, oh, 4 coulombs has arrived, and then multiply that by the 45 newtons per coulomb warning. But to do that, you would need to say, oh, hey, look, I'll reveal the little cover here and say, oh, yeah, 4 coulombs has come to the party. Now, the second half of the chapter, with its two cornerstones of the chapter, potential energy. So we try to put a little P on here if we remember, just so that we don't confuse it with electric field. So it's kind of unfortunate that we have those two quantities in the same chapter, both with a capital E. So the potential energy of Q2, that doesn't really make sense grammatically unless I say and Q1, because it's a handshake, this whole energy thing. So potential energy between 1 and 2, you would be calculating that by going K, Q1, Q2, all over just a plain old R. The value ends up being, in this story, positive 2,700, and it's an energy, so the units would be joules. Now, as far as the plus and minuses go, it's just a scalar here. We don't have any direction like north and south, but we do have plus or minuses, and this is where you trust the math. The math will figure out whether the answer needs to be positive or negative. Just simply put in positives or negatives for the Q's. Watch out in that denominator, because down here it's just R. Nothing gets squared. So that's potential energy. Now, the thing we're looking at today is not potential energy, but what about potential, right? It's like you're not quite saying the word potential energy, just saying the word potential. So this is the same thing as somebody saying, hey, what's the voltage at that location due to Q1? You know, we want to warn people that Q1 would create some energy on a Q2 if it arrives. So potential voltage, number 1, would be K, Q1 all over an R. The answer ends up being positive 675. Now the units. Yes, we will eventually say volts, but you should always be thinking to yourself about what that means. Joules of energy for every coulomb you choose to put there. So yeah, sure, we would actually probably write this as 675 volts. But that's not how we think about it. We think about it as joules for every coulomb. Trust the math on that only Q that you get to put in there. If that Q is negative, then go ahead and put a negative value in. And this one was positive, so we put a positive value in. The R, just R, nothing squared, plain old R. The reason for doing that 675 volt number, hey, it lets you quickly figure out energies. So if somebody says, oh, I really need to figure out potential energy between 1 and 2, great, tell me what the Q2 is as it arrives and I'll multiply it by voltage 1. I will have done a lot of the work already. I'll get you to your 2,700 number. We can get to that amount of energy just by taking the 4, the Q2, finally arrived to the party, and multiplying it by the 675. Okay, 2 more pages here. Sometimes we talk about changes in voltage when we're playing this game with electric potential. It's a really, really handy thing, this idea of changes in voltage, for quickly measuring changes in potential energy. If you've got a story where you want to measure change in EP, then measuring change in voltage can really help you out with that. And we're going to see that here on the story that we're going to do. So we've got a Q1 that's already been sitting there for a very long time. And then there are 2 places where at the beginning of the story, nothing is positioned, just these markers, A and B, 15 meters, and then 3 more meters down the road at 18 meters. And the question is, what's the work required to move an electron from A to B? I don't actually need the idea of voltage to do this, but I want to show you how it can help. So here's how you can do it without worrying about voltage. You could say, well, if I look at this story, let's go to the top of the page here. I've got potential energy when I'm at location A because I'm 15 meters away and not infinitely far away. I have no speed, perhaps. I'm going to do some work, and I'll have potential energy when I'm 18 meters away. In fact, I'll have potential energy until I'm infinitely far away, so I'll certainly have some at 18, but it doesn't say there's any speed. So it looks like the work is just EPF minus EPI. So I could write that as the change in EP, right? That would be final minus initial. Change is always assumed to be that, right? That you would go final and subtract off initial. And in this story, you would be going K, Q1, Q2, which would actually be the electron, and then you would be dividing by, now this is the final story, so this is the 18, minus K, Q1, Q2, all over the initial R of 15. And I just want to tell you that the number is actually positive 1.8 times 10 to the negative 17 joules. That's correct, it's the right value, and you can get there by doing nothing but looking at changes in potential energy. It does make sense that it's positive. It makes sense that it's tough to move an electron away from that Q1. They were attracting to each other, so it does not want to leave, and you're going to have to push it pretty hard. Okay, now we're going to do that same question again, but in 2 steps. First part, what is the potential difference? That's like saying, hey, what's the voltage difference between those 2 places? Now remember, voltage warns you about potential energy. So you could go and find the voltage at A. You would be going K, Q1 all over 15, and that ends up being 675 volts. Okay, great, that's the voltage at A. Now, let's go and check out what the voltage is at B. How much possible energy is there at B? Well, I would go K, Q1 all over 18, and that voltage is not quite as big. It's around 562 volts. Okay, well, this question is saying, can you go find the potential difference, the voltage difference? Sure, we can do that. So the change in voltage would be the final voltage B minus the initial voltage A. And if you subtract those values, that change in voltage ends up being negative 113 volts. And at first glance, we might be looking at that going, well, how is that helpful? Like, it just sounds like we've just made a whole bunch of work for ourselves trying to come up with this value. But I want to show you how this change in voltage of negative 113 volts can actually speed things up. So here's the same question again. What's the work required to move the electron from A to B? Okay, well, looking at that story, that equation at the top of the page, it looks like we just have to find changes in potential energy. But I know this. I know that potential energy in general is the Q that finally arrives, the Q2, multiplied by voltage. And if that's true in general, then it seems pretty reasonable that changes in potential energy, if you're motivated to find those, would just be the Q2 multiplied by the changes in the voltage. So here's a super fast way to do this question. Instead of saying, oh, wow, you want to find the work, you're going to have to go and look at potential energy. You can, right? You could say the work is just going to be change in EP. It's going to be EPF. We did this at the top of the page. Minus EPI. Yeah, you can do that. You'll get your 1.8 10 to the negative 17 joules. But instead of doing that, you could say, oh, the work is Q2, thanks for finally showing up to the party, multiplied by the change in the voltage from that charge number 1. And totally trust the math here. So if you're going to move an electron, the Q2 is negative 1.6 times 10 to the negative 19. I don't usually put the units in, but I'm going to put them in this time. I usually wait till the end. Coulombs multiplied by the voltage change. Well, that's right up here, right? There's the voltage change. So I could put in minus 113. I could write volts, but I want to think about what they mean. Joules per coulomb. Okay, great. Multiply those out, guess what you get? 1.8 times 10 to the negative 17 joules. So it's just an option that allows you to find the work involved when that work story makes you need to find change in potential energy. You could instead just go and find the change in voltage, or maybe you know the change in voltage, and then you can multiply that by the Q that's actually moving around. Okay, last page here of the day. Let's go, I think this is the last page. Let me just double check. Yeah, it is. Let's go and look at example 1 here. So example 1 says, hey, can you go and sketch the voltage near a 3.6 microcoulomb charge? And you might say, well, near which way? Above it, below it, behind it, in front of it, on top of it? Doesn't matter. Voltage doesn't care which direction you are away. It only cares about how much you are away. The equation says that the voltage is equal to KQ simply divided by R. And the R is just us measuring how far you are away in any particular direction. So we're going to do a little graph here showing the voltage, the warning about energy as you get close to some charge. And I don't really care which way you arrive. In a graphing sense, if you're trying to think like, how could I do this maybe on my graphing calculator? You could imagine that this looks like something you'd put into your calculators, maybe like y is equal to some constant divided by x. And we want to see how does that vary as the x goes bigger or smaller. And the answer is it gets really large when the x is small. So the voltage, because of that R in the bottom, is going to get really big when we're near the location of this 3.6 microcoulomb charge. Now I know this graph makes it kind of look like I'm approaching this pink 3.6 microcoulomb charge from the left or the right. I just want you to think about it as approaching it in general. And what happens is the voltage just starts to skyrocket like an asymptote, like that. It actually kind of looks like a volcano in multiple dimensions. All right, it should look like a symmetric volcano though. Let me try that again. Not bad. So there's the graph of voltage near a charge. The voltage gets really big when you get near that charge and diminishes down to 0 when you're infinitely far away from that charge. Part B says, hey, what's the voltage 12 meters away? Okay, I don't know. We'll call this voltage B because it's question B. So I would be going K, 3.6 times 10 to the negative 6, and then 12 meters away. I tried that out. I actually ended up earlier getting positive 2,700. It's joules per coulomb, but we could just say, yeah, volts, right? But it's warning us about energy if you happen to be 12 meters away. Again, I don't care whether you're 12 meters away this way or whether you're 12 meters away that way. It doesn't really matter. When we're that far away, if you check out the level, this is at 2,700. Okay. 2 follow-up questions. Part C. If a proton is released from rest from 12 meters away, how fast will it be going when it's really far away? Well, that's kind of like taking a proton, we'll bring it nearby this pink charge, we'll put it right here, and then letting it go. It's going to go rocketing away in this direction. It's going to pick up speed, most of its speed at the beginning. And the force changes though, so you'd want to attack this from the point of view of conservation of energy. I'd be going, okay, EPI plus EKI plus any work from an ELF is equal to EPF plus EKF. Well, it didn't say it had a running start. In fact, it said it started from rest, so no EKI. And then it said, oh, we're going to be very far away in the end. Well, that means there's no potential energy in the end. There's also no ELF, so we can throw that away. And so what we have is potential energy being converted into kinetic. And the reason why I wanted to show you this graph, not only is it a kind of a required learning outcome that we know how to graph that, but you can think metaphorically of the proton being like a rock that would roll down a hill like a volcano like this and pick up speed. So positive charges like to roll away from high voltages and then pick up speed as they leave. And that volcano, that voltage graph gets infinitely flat when it gets infinitely far from that 3.6 microcoulomb charge. So the values, if I wanted to find potential energy, yes, I could go K, Q, Q all over R. But hey, look, I already figured it out in part B here, right? I had that VB. Why don't I just save some time and go QV is equal to kinetic energy, 1/2 m little v for velocity, lowercase, squared. And so you would have a Q of a proton, 1.6, 10 to the negative 19, and then the voltage of 2700 is equal to 1/2. Now I'm going to save a little space here. I'm just going to say MP, mass of a proton. You can go look that up. And then speed squared. I don't even know what the answer is. I don't care. Instead, I want to just sort of highlight that the proton, much like a rock rolling down a hill, it, if I can use the verb, falls to lower voltage. So protons and all positive charges, they fall to lower voltage. They will just naturally, spontaneously do that and pick up speed. Electrons, on the other hand, are not like rocks rolling down a hill. They're like helium balloons. They like to go up into the sky. In fact, it's hard to pull a helium balloon out of the sky, and that's much like the electron. So the electron is released from rest, from really far away. How fast will it be going when it gets 12 meters away? So the electron starts way out here, and it's going to get to a point where it's here and going really fast. So it actually desires to get close, if I can say it has a personality. It wants to get close in a force sense to that 3.6 microcoulomb charge. It's like a helium balloon rolling up a hill, up this metaphorical voltage volcano, and actually picking up speed right as it goes up into the sky. And so final example of the day here, the force changes. It becomes a bigger and bigger force as you get close. So don't try to do forces and kinematics. In fact, how would you when you're infinitely far away, right? What would you put in for the D, right? It's not going to work. So instead, we want to do conservation of energy. I'm just going to lay it all out. EPI, EKI, plus work from an ELF, EPF, EKF. All right, we start infinitely far away, way out where that voltage volcano, the warning about energy is flat, so there's no potential energy at the beginning. We also start from rest, so there's no EKI. And there's no story about an ELF. So, whoa, we just lost the entire left-hand side. But that's okay. We're going to end up with 0 energy is equal to QV plus 1/2 mv squared. And at first glance, you might look at that and go, that's not going to work. But no, it's okay. Trust the math. We would have 0 joules in total is equal to, now this is an electron, so negative 1.6, 10 to the negative 19 for the Q for that thing. And then the voltage, we already know, 2700 plus 1/2. Again, I'm going to cheat here a little bit. Just put ME, mass of an electron, because I don't have room. And then the speed squared. So instead of actually telling you the number, I'm going to do two things instead. I'm going to say, just in my little air quotes here, that electrons, and this is also true for any negative charge, electrons, they just do this spontaneously. Electrons fall to higher voltage. They seek higher voltage. They will pick up speed as they go towards a higher voltage. Second thing, I just want you to think about which of these two stories, part C or part D, has a bigger velocity. Turns out they both have the same amount of energy to work with. They attack that story from different directions. The proton leaves the 3.6 microcoulombs and the electron arrives. But if you check out the value of this number, okay, the number of joules we have access to, and the value here, okay, sure, we had to kind of be creative about what side to put them on because the electron's negative. But that value is the same number of joules that they have to work with. But one of them goes way faster than the other, and it's the electron because it's so light. The electron's mass is about 2,000 times smaller than that of a proton. So it's going to take all of that energy, and it's going to end up going really, really fast. So you end up with a faster speed in the end. And again, key thing, the force was changing. That's why we had to do conservation of energy and could not do simply forces and dynamics. That's going to be the end for this video here, I think. Let me just again double check, make sure there's not another page here that we needed to do. Nope, that's into the last day. So we're all done right here.